Go get started. So welcome back, guys, to EE240. Looks like we've got some other classes with exams or something decimating our attendance here, but hopefully it'll pick up as we go along. So any kind of questions or anything like that before we kind of dive in? Or how many of you guys here have started the project? 1.5. Okay, so as I said, you really need to get going because there's actually quite a bit of stuff that's going to have to be done there. And you're going to know everything you need to know by within the next like 30 minutes or so. So make sure you do that because, again, you know, the number one thing that I hear back from people is, oh, I wish I had more time. So that's why I delayed the due date, but you know, there's only so far I can do it because the final exam is very shortly thereafter that. So again, you know, I strongly urge you guys, make sure you go ahead and get started. So for those of you guys who did, good job. You know, you'll thank me for it later. If not, trust me, start, because again, you'll thank me for it later. Just a couple other sort of logistics things. This is perhaps obvious, even though next week is, you know, technically the reading relaxation or something. I forget what the third R is. It's a graduate class, so we're going to keep going with the lectures. It will be sort of stuff that is actually important and interesting for you to know. It won't be directly related to the project, but make sure you do show up. In particular, please do show up next Thursday, because that's when we'll do the course reviews with Eta Kappa Nu. So, you know, of course, I'd like to get everybody's feedback. So on Thursday, I'll make that sort of mandatory attendance. You shouldn't have any other classes going on, so it should be easy for you to actually show up here in person. Yeah? Yeah, I'm still going to have the normal office hours next week. I might even add some office hours towards the end of the week, given that the project is going on and that you guys will be doing the presentations on Monday. But yeah, I'll definitely be around, and so, you know, you should definitely feel free to come by and bug me. And we'll also, for next week, we'll sometime, probably not next week, but we'll schedule when the review session and all that will be for the following week. Because again, the final will be on, I think it's Wednesday, May 12th or something like that. So just keep that in mind. Okay, any other questions on either material we've been covering so far or the project or anything like that? Okay, so maybe I'll put it this way. So by, you know, next lecture, I expect that there should be tons and tons of questions on the project because, you know, I didn't necessarily specify every last thing that you should be doing. So make sure you show up with, you know, at least one question per person from the project on Tuesday, because I may call on you and, you know, I'll have a grade for whether you have a question or not, and deduct that from your final exam score or something if you don't have a question. So make sure you do that. Okay, so unless there's any other sort of questions on the stuff we've been talking about so far, we can sort of go ahead and dive back in. So last time we were really talking about basically how are we going to deal with offsets. And at the beginning of the lecture, I kind of mentioned there's really sort of two broad categories. So one was essentially trying to treat the offset differently than the signal. That usually meant either somehow taking the derivative of the offset, or somehow basically modulating it to a different frequency so that it basically didn't affect the actual signal that we cared about. So the other big category, which is really what I'm going to talk about today, and really what you're most likely going to use in your project, is so-called sort of trimming. And what that really kind of means is, let's just somehow at the beginning of operation measure what the offset is, then inject the signal back to cancel it, and then hopefully just leave that signal there sort of during the entire time that we're going to be operating. Okay, and in fact, I kind of claim that we sort of saw something that at least conceptually might lead us down this path already. Okay, so if you guys remember, we talked about that, you know, auxiliary amplifier idea. So let's kind of go back and take another look at that one. Okay, so let's imagine that basically during some startup or some sort of initial calibration phase, we just take our amplifier. We, of course, ground the input, where, again, ground just means effectively zero differential. And then we just, as we had talked about before, we basically use an OTA to just try and integrate what the output is, and then feed that back to the negative input. Right? So this OTA here, the idea here, this is just integrating the output. Right? And just as a reminder, I want to build an integrator here because I want to make sure that I have zero residual DC offset, right? Because an integrator has infinite gain at DC. Okay, so during startup, I sort of tie my circuit up like this, and again, the idea being just that I'm going to somehow figure out, you know, if there's some offset over here, I'm going to inject the appropriate amount of offset onto this negative input so that the output goes to zero, right? Okay, so once I've done that during the startup, then during operation, of course, I want my normal input signal, right? So I'm actually going to connect that into my amplifier. I still want to be sort of canceling that offset. So I need to sort of store that, and let's say that V off appears over here. Then it should still be sitting over there. But now I'm just going to sort of disconnect that feedback loop, right? And again, I'm going to disconnect there because during the normal operation, I don't want this feedback loop actually throwing away the DC part of my signal, right? So I just want to basically keep the offset around, but I don't want to have any effect on the signal itself. Okay, so conceptually, this is all really that sort of offset trimming is doing. It's just somehow during some initial phase, you figure out what the offset is, then you inject some signal to oppose it, and then you just try and leave that signal there during the time that you're operating. Okay? So now, I kind of drew this with this somewhat conceptual thing, but let's say I really tried to build it the way that I've drawn it here. Anybody see any problems with this? Do you think this is really going to work, or? Any thoughts?
Cap will bleed off.
There we go, right? So let's say that I wanted, okay, I do some startup, and let's say I started the thing up, let's say it's my laptop. I started the thing like a day ago, right? And I just want to keep, I don't know, I'm on a marathon project working session for 240 or whatever it is, and I want my laptop to run the entire day, right? Well, okay, and, if I even have like a femtoamp of leakage off of that capacitor, most likely I ain't going to have the voltage, or in fact, I'm definitely not going to have exactly the voltage that I put onto it a day ago, right? In fact, unless I have a really big cap with like a femtoamp of leakage, pretty quickly you ain't going to have nothing at all on that cap, right? It's just going to completely leak away, okay? In fact, not only that, you can imagine even just sort of the components inside, like the comparator itself, might drift some over this time, right? But really, more importantly, if I do something like this, I'd have to somehow build effectively a zero leakage switch, right? I'd have to make sure that that voltage is just staying there kind of forever. Well, okay, there's maybe some really wild and crazy like MEMS stuff you can come up with to do this, but in CMOS circuitry, sorry, ain't going to happen. Okay, I mean, actually, if you're really, really good, you could maybe get this to stick around for a second. But even that is actually pretty darn tough to do, especially with modern transistors. Okay, so conceptually, this is actually what we're going to want to do. But most likely, we're not really going to build it this way. So anybody have an idea what's a nice way of sort of keeping things around for a long time, as long as the power supply is around? What's like, what kind of circuit could you build that would keep stuff around for a really, really long time?
Register, latch kind of?
Yeah, I want sort of like a latch, right? By the way, those latches usually have digital signals in them, right? Because just at least conceptually, if I have a digital thing, just take two inverters and tie them back to back. And if I manage to get a 1 and a 0 into there, it'll stay a 1 and a 0 as long as I have the power supply on, right? So basically, what we're actually kind of saying now is that what we really want is effectively some sort of digital way of storing the offset, okay? Not only, of course, storing what the value is, but then once we've stored it, we want to somehow correct that. So the idea then is actually sort of fairly simple. So again, I'm actually going to take my same amplifier. Okay, so that's... But now instead of tying it sort of through a negative feedback loop that estimates the offset sort of in an analog way, what I'm going to do is I'm going to build basically the equivalent sort of digital or let's say mixed signal implementation. Okay, so let's actually work away from the output. So if I wanted to somehow sort of digitally estimate what the offset is, what sort of component should I first add in all the way back over here? Just conceptually, what am I sort of looking for over here? What am I trying to convert from what to what?
Analog to digital.
Yeah, right? Basically, what I want is something that's going to tell me, okay, the analog voltage that you have sitting over there, I just want to convert it into some digital code, right? Okay, so I'm going to have some digital code over here. If you guys remember, I said a second ago that, when I built this thing, I basically wanted this OTA to act like an integrator. What would be the equivalent thing I'd want to do here in the digital domain then? How would I sort of like integrate this digital code to try and force it to go to 0? Or maybe just be more simple. How would you integrate that digital code? What does integration sort of mean?
Add.
Say that again?
Add.
Yeah, okay. It's called an accumulator, right? So if I had, let's say, a 1 coming in out of this thing, I should add 1 to my previous code. If I have a 10, I should add 10 to my previous code, and so on and so forth. Right? So basically what I add into here is an accumulator. Okay? Now, once I've got that accumulator, I need to just turn basically that integrated value back into an analog voltage. Right? So I just put a DAC right there. Okay? So again, essentially, really all I'm trying to do, all these 3 blocks right here, I'm just measuring the offset, converting it to a digital code, integrating that measured offset, and then subtracting that integrated value back off to try and just recreate whatever the offset is right at that point right there. Okay? So now the advantage of this is that during startup, again, I just ground the input. I run this little loop here, right? I basically will come up with some digital estimate for what my offset is. Then when I'm done, I just stop the loop. I store that digital code there just inside of my flip-flops or the memory or whatever it is. And as long as I've got the power supply sitting there, it should stay there basically forever. Right? So nice. Now I've at least gotten rid of this sort of leakage problem. So now there's kind of a couple of, let's say, interesting questions here. So the first question I want to ask is, how much resolution do you need in the DAC? And by resolution, I kind of mean like the number of bits. Or more precisely, like, well, actually, it's really 2 things. It's the number of bits and like how small do the step sizes out of that DAC need to be. So what do you guys think? And by the way, I don't mean a number. I mean more conceptually. What's going to set sort of the resolution of my DAC there?
Gain of your amplifier.
Okay, you said the gain of the amplifier. I might be able to back it into something like that. But I think there's maybe a little bit easier way of thinking about it. Ah, the offset. What about the offset?
Like it has to be like smaller than V offset.
Ah, okay. You're actually going in very much in the right direction. So let's just do an example. Okay. So let's say that I expect that the offset I'm going to get right here is 100 millivolts. Okay. Let's say like 3 sigma or something like that. It's going to be 100 millivolts offset. Right? Okay. So first of all, what's the range that this DAC is going to need? I don't even know how many steps I need yet, but what's the range I'm going to need?
100 millivolts.
Yeah, actually plus minus 100 millivolts, right? Because 3 sigma is, plus 100 millivolts. There's another minus 3 sigma on the other side. So I need a range of like plus minus 100 millivolts here, right? Now, let's say that I just arbitrarily choose my step size to be 10 millivolts. I'm just making it up. But let's say that my step size is 10 millivolts. What's that going to say about my residual offset once I've run this loop? How big is it going to be? In other words, how much offset am I going to have left over?
10 millivolts.
Yeah, I'm going to basically have 10 millivolts, right? Because essentially, since this thing only has discrete steps, but here, this can be anywhere between 0 and 100 millivolts, or actually minus 100 millivolts and plus 100 millivolts in analog steps, right? Then essentially, whatever step size I use in this DAC, basically I can always only estimate it to within like 1 digital code, right? So I'm always going to be jumping back and forth between that digital code, and if it's not quite clear to you, I'll show you an example in a second that'll make that really more clear. But basically, what's going to set the resolution of this DAC is really how big of a residual offset are you willing to tolerate? Okay? So in fact, you could actually claim that that's related to kind of the gain of the amplifier, because obviously, if you have a high gain amplifier and you have like 10 millivolts of offset left, you might still be railing out the whole thing, right? So really what's setting the resolution of that DAC is basically the residual offset and the range of offset you need to cover, right? So let's just use this specific example. Let's say I indeed wanted 10 millivolt steps with plus minus 100 millivolts of range. Roughly how many bits do I need?
4.
It's actually about 5 because it's plus minus 100 millivolts, so it's about 5 bits. Really, it's about 20 steps, but that would be like about 5 bits, right? Okay, and then obviously if I wanted to do like a millivolt of step size, I'd need something like about 8 bits, right? Because I'd have to take 1 millivolt steps with 200 millivolts of range that I need to cover, okay? Okay, so DAC, basically what's setting that is residual offset plus the range of the offset. Okay, so you can see pretty quickly, if you want really small residual offset and you have a pretty big range, you need a lot of bits in that DAC. Okay? Now, here's another interesting question, or really the next interesting question. How much resolution do you need in the ADC? Do I need 8 bits in that ADC too? What do you guys think? Let's maybe take a vote. Who thinks you need just as much resolution in the ADC as you do in the DAC? Who thinks you can get away with a lot less? 3 people. Okay. So why can you get away with a lot less? I agree with that, by the way. So how come you can get away with a lot less?
Because your accumulator integrates your error.
Mm-hmm.
So to wait longer, you can integrate more.
Okay, so you said your accumulator is kind of like integrating the error. So even if I make this sort of lower resolution, if I wait long enough, this accumulator should sort of get to the right spot, right? But that's actually basically the right idea. Okay, so in fact, and we'll maybe just draw this in 1 second now. If you guys remember, where is the offset where have we been talking mostly about it in terms of it really bugging us? It was the comparator. Well, guess what? A comparator is an ADC. Okay? It's a 1-bit ADC, but it's an ADC. So in fact, I claim that we can actually build this offset cancellation loop without adding any additional ADC into it. We can just use the comparator. So let me just draw sort of an example of how that would look. Okay, and I'm drawing it sort of in single-ended things now, but remember all these are really probably differential. Okay? So I have my comparator here. It's going to have some digital output. Then, just like before with the ADC, we just accumulate that digital output, which again, this digital output here just means 1s and 0s. Then I take the output of that accumulator, I feed it into a DAC, and I feed that back into the negative input of the comparator. Right? Now, just to be sort of really clear, technically, to do this sort of right, there should be some switch here to ground the input so that when I'm doing it during calibration, I really have 0 input. But again, I'm assuming you guys kind of remember that from before. Okay? So let's maybe sort of take a look at how this thing would just conceptually work. So let's just say as an example that initially the offset is such that my digital code is a 1. Okay? So basically I sort of clock this comparator thing, and my comparator says that the output is a 1. So then what would the DAC start to do? What would the output code from the DAC do on the next clock cycle? And let me just label this. Let's call this V DAC. What would the DAC do? Let's say that the DAC output started at 0. Which direction would the DAC output start moving if my output of the comparator was a 1?
Up.
Yeah, it'd move up, right? So if it used to be 0, it'll take a step up. Well, then on the next clock cycle, if my comparator still says it's 1, it'll take another step up, right? So basically, as long as I have a 1 coming out of the comparator, I'll be taking steps up out of the DAC, right? Now, eventually, what's going to happen? What happens when this DAC voltage gets larger than the offset of the comparator. So just, I'll draw it in here. Let's say that the offset of the comparator is maybe, let's say that that's where the offset is. Okay? So, what's going to happen once I hit that point?
Flip.
Say that again?
Flip.
Yeah, it's going to flip, right? So the output of the comparator, once I clock it again, will go to 0, right? Well, once it goes to 0, the output of the DAC will go back low, right? All right, what's going to happen on the next clock cycle?
Go back up.
Yeah, it's going to go back up, right? Comparator's going to say, oh, no, you're too low. It's going to go back up, and now obviously you can kind of get the idea. It's just going to go back and forth like this, right? It's just going to jump back and forth and jump around whatever the offset level is, right? Because I can't get exactly to the offset, but I can get so that I'm jumping around it, right? So now here's kind of a, maybe not the interesting question, but sort of just another way of maybe thinking about things. So if I looked, once I've sort of canceled the offset, once I'm sort of jumping around like this, what can I say about sort of like the average value coming out of the comparator? Or what can I say about like the number of ones versus the number of zeros? What should it be? Yeah, they better be the same, right? Because basically, if the number of ones is not the same as the number of zeros, that means that actually I'm not jumping around this point, right? Because essentially, if I'm really jumping around that point, I should just be going back and forth, back and forth, back and forth, right? Now, by the way, I've sort of drawn this deterministically in the sense that, over here I've said that this was always a 1. But you can imagine if there was some noise around this, maybe I would have occasionally gotten a 0, right? But certainly it's the case that even if I got a 0 like occasionally close by, it better be true that I get the same number of 1s and 0s, otherwise I'm really not canceling the offset, right? Because that's the only way really that I could be sort of sitting at the center point where this accumulator is not moving anymore. Right? Because if I have more 1s than 0s, the accumulator is on average going to move up, right? Okay, so that's basically how this thing is working here. And again, notice I really didn't need any more information than just which direction should I go to try and cancel the offset, right? Once I know that and I can make small enough steps, I can actually get this whole thing to work, okay? So just to make sure it's sort of really clear to everybody, I just want to draw sort of one more picture that kind of gives us an idea of what it is that we're doing, right? So if I just sort of look at the transfer function of the comparator, if it has some offset in it, all I'm basically saying is that essentially I've shifted that 0 point. I've shifted the point at which you flip between giving a 1 output and a 0 output, right? So all this loop here is really doing is saying, okay, if I give you an input that I know is 0, then let me just see if you give me a 1 or a 0 at the output. If you give me a 1, I'm just going to push the offset back towards 0, right? If you give me a 1 again, well, I'm going to push you again back towards 0. If you're still giving me a 1, okay, I'm again going to push you back towards 0. Well, once you've done that, once you've gone all the way across 0, now your comparator should give you the opposite output, right? So in that case, it's going to go back the other direction, right? So now, once you're basically done, you can kind of see you should just keep tracing out that loop right there, right? So you should just keep jumping between basically having your offset there versus having it sit there, okay? Does this sort of make sense to everybody, or? Okay, so again, this is actually most likely how you're going to do things in your project. You don't need to build the accumulator, by the way. You can assume that some magic digital guy gave that to you, okay? Because it's not actually all that hard, because you don't even have to really run it all that fast. But you'll definitely need to build this sort of DAC. And so what I'm going to spend a little bit of time talking about is just how you'd build that DAC, and basically what are sort of some of the considerations in terms of actually building that DAC. Okay? No, so you don't have to implement the feedback loop. You can just, because remember, you're just going to be sort of putting in worst case offsets anyways. So you can kind of figure out on your own what the code for the DAC really should be. If you're lazy and you want to write just some Verilog block or whatever it is to build the accumulator, I have no problem with that, but you don't need to. What you do need, however, to keep in mind is that there's only a finite resolution you can actually get out of that DAC, right? So even though you're not actually going to be building this whole thing, don't sort of abuse the system. In other words, don't give yourself like 20 bits of resolution here, because that's probably not really going to happen. Okay? So try and figure out what's kind of a reasonable thing for you to do. Yeah.
So for the power, do we need to try including the power of the DAC?
Ah, absolutely. So I'm going to talk some more about that in 1 second, because sorry, no free lunch, right? The DAC is going to do something. Now, so we're going to talk in a second about how you'd really build this, what this DAC might really look like, and therefore how much power it might actually be burning. But absolutely, whatever this DAC is doing from both a power standpoint, from a capacitive loading standpoint, all of that stuff, you have to actually include. Okay? The other thing that, again, you should sort of think about is when you build this DAC, you remember I said that there was always like offsets and mismatch between transistors? Well, you should include those offsets inside of the DAC too, because it's going to mean that basically you're not going to be able to set the code as precisely as you would have wanted. In other words, even if you build a DAC that you think nominally has 10 millivolt size steps, when you include the mismatch, you might actually have 15 millivolt steps, or 20 millivolt steps, or whatever it is. Okay? That basically means that in the worst case, you're not really going to have the step size you designed for, but you're actually going to be jumping between your two biggest, or really between the two codes that have the biggest step between them. Okay, that's really what's going to set the worst case residual offset. Okay? And by the way, just in case you're wondering, if you just so happen to have one code that was right here, sorry, you can't use that one because you don't know whether you'd really land there or land on the code right next to it. Okay, so you always basically get one full step of potential error just because there's no way for you to really know which side should you be on. Okay? Yeah.
If ours exactly happen to be halfway.
Yeah, that just means you happen to get lucky, and if you measure a different chip, it won't be that way.
Okay.
I mean, unless you have some really, really high resolution DAC or you're doing something much more clever than I know of, but basically it's random, right? You really don't know where the actual offset's going to be, so I just have to tweak that offset ever so slightly, and you'll get the full step of error. That's a good question.
So we actually need to guarantee that our DAC is monotonic, right?
Ah, that's a very good question. So I'm not going to sort of push you too hard on it, because this, after all, this isn't meant to be a class about designing DACs. But you're absolutely right that if your DAC is non-monotonic, which it just means, for those of you guys who haven't heard of this before, if I do a plot of the voltage out of the DAC versus the digital code going in, if you ever had something that, as an example, did that, which, by the way, can certainly happen with mismatch, then the bad news would be that if you ever happen to need this particular set of codes here, you might end up jumping between those two spots. So you're absolutely right that when you build these offset cancellation DACs, usually the number one thing you care about is, I mean, monotonicity is actually important, but more so really, you just really care that the step size is small enough. Okay, non-monotonicity is kind of annoying because you can indeed end up sort of jumping around between more than one code. So a lot of times you'll take steps to avoid that, but much more so, you just want to make sure the step sizes are small enough. It's a great question. Any other questions on this? Or? Okay, so let's actually sort of talk a little bit about how we'd really build something like this, and just really what are the sort of main issues to think about. So what it really all comes down to is essentially how do you introduce some sort of digitally controlled offset into your comparator. Okay? Now, turns out there's basically an infinite number of ways you could possibly do that. Okay? Because just about anything you can think of could create an offset. And so therefore, you could intentionally do just about anything you can think of to create that offset. Right? That doesn't mean that all of them are actually good ways of creating that offset. Okay, now, so people have tried just about everything that you can think of to make those offsets. I'm going to just spend a little bit of time talking about what I think are the maybe let's say the most interesting ways, and really just what the trade-offs are, what the issues have to keep in mind. So really some of the key issues that we've already touched on is, first of all, just how much power are you going to be spending to create that offset, right? Because after all, that offset is just DC, right? So when we spend power to cancel it, it's kind of like annoying, right? Because that power is not really helping us get higher bandwidth or lower noise or anything like that. It's really just canceling the offset. The other thing which tends to actually be very important in terms of canceling these offsets, or really these trim types of things, is how much imbalance are you introducing into the circuit? In other words, we did all this work to kind of build these differential circuits, but basically, pretty much intrinsically, to introduce an offset, that means that we're imbalancing this thing that we tried to make perfectly balanced. Okay? So this is really kind of one of the key issues here. And just to kind of give you an idea, the reason I say that is because anytime you introduce that imbalance, then all of the kind of good stuff that we said we were going to get from differential may not be so good anymore. So as an example, let's just say that the way I built my offset was I just somehow tweaked the two load resistors, right? So one side I made it 2 kiloohms, the other side I made it 1 kiloohm. So what would be sort of potentially bad about doing this? What sort of specs might I be giving up on? From the standpoint of this differential amplifier.
Differential to common mode gain.
Yeah, exactly, right? What I'm basically giving up on is the common mode rejection ratio, right? And similarly, the power supply rejection ratio, right? Because basically, since it's now intrinsically imbalanced, if I put some common mode input into there, it's going to create a differential output. If I move this power supply around, it's not going to couple the same way to these two sides, right? So again, it's going to create some differential output, okay? So those first two ones, those are kind of like the key ones really from a kind of circuit performance standpoint. But of course, the other two are probably equally important. We've kind of touched upon it a little bit already. You care a lot about just what's the effective resolution you get from creating these offsets. In other words, per digital code, what's kind of like the biggest step you might get coming out of this offset, okay? And then the last thing, as you might imagine, is just how much area is it going to take you to actually build this darn thing? Because we already calculated just off a back of the envelope. We said we had like 100 millivolts of offset, and we wanted to cancel it down to like a millivolt or so. It's an 8-bit DAC, right? If I need a lot of these comparators with a lot of these 8-bit DACs, that can really start to add up from an area standpoint. Okay? So those are kind of the key things to keep in mind. So, with those in mind, let's maybe just walk through a couple of example offset cancellation schemes. And I'm going to draw these for the strong arm comparator, but you can imagine you can apply very similar techniques to either the CML latch or just about any other type of comparator design you can come up with. So let's just start out first with our sort of bare strong arm comparator. So I'm just going to draw the comparator here, and then I'll show you sort of, let's say, a first cut at what we could do to actually cancel its offset. Okay, so this is like the core of my comparator, right? So if I wanted to introduce some sort of offset, basically all I have to do is, again, somehow imbalance the two sides, right? So actually one of the, maybe not first, but one of the main ones that, one of the main techniques people use to actually do this at first was a little bit funny. So I'm actually going to draw it. So essentially what people initially did was actually add into the two sides some variable amount of capacitance. Okay? So effectively, if you wanted to create, one sign of offset, you'd turn on some extra caps over here. If you wanted to create the other sign of offset, you'd turn on some extra caps over here. Okay? Now, the way this works is a little bit funny. Because if you guys remember, we had talked about how this comparator works. Essentially, first, you just integrate some current off of these transistors, right? And that creates a voltage difference. Well, if the two sides have a different amount of cap, then for the same input voltage, you'll get a different voltage, the same input voltage over here, you'll get a different output voltage, right? Because the same current would integrate onto two different capacitors, okay? In fact, not only that, once you start regenerating, if you guys remember the regeneration time constant is always Gm over C. Well, if the capacitance on one side is different than the capacitance on the other side, that means the regeneration time constants are going to be different on the two sides. Actually, I guess this is tau inverse, is that, right? So in other words, what I'm doing here is by sort of turning on extra cap onto one side or the other, I'm just sort of trying to tweak the effective gain from the plus side versus from the minus side. And when I do that, if I tweak it just right, I can basically cancel any offset that I'm getting, let's say like this, from the input devices, or actually from the overall comparator. Okay? Does this kind of make sense to everybody in terms of just how this works? Okay, so now, here's the kind of key questions. So, hopefully you believe me or you understand I can create an offset by doing this. Why do I claim that I probably don't like this all that much, in terms of how to actually build it, in terms of what you pay to actually build this? What's the bad news about this?
Slowing it down.
Yeah, you're slowing it down, right? Because I'm adding these extra capacitors here. So certainly when I turn these switches on to create that offset, I'm going to add extra cap. So I'm definitely slowing it down, right? That's certainly true. In fact, even when I don't have these switches on, remember, all capacitors actually have some parasitics, both from the top plate and from the bottom plate. Right? So if I add a lot of those caps on, I could be adding a lot of parasitic capacitance right onto my output of the comparator. But remember, at the output of the comparator, that's exactly where I wanted to have as small of a cap as I could. Basically, as high of an FT as I possibly could. Okay? So that's bad. I'm basically slowing myself down. So what else is bad about this? What do you guys think? What are kind of the key things I care about in terms of just offset cancellation in general? I'll give you a hint. There's a list over here. So any of these, what out of these list of 4 things that I put here, which ones is this one bad?
Area.
Okay, area maybe. Yeah, it could actually be pretty big because I have a bunch of these caps that I'm adding and switches and things like that. I'm not sure it's necessarily worse than some of the others, but that's certainly extra area. What else?
Power.
Okay, yeah, I'm definitely adding power, right? Because to get the same speed, since I have more cap, I'm just going to have to burn more power. That's definitely bad. Anything else? There's only 2 more things on the list, I guess, so. So what else? How about this one right here? How am I doing from that standpoint? Is my circuit still balanced if I have, 10 picofarads of extra cap on this side and my whole thing only used to have, I don't know, I'm just going to make it up, but 10 femtofarads? No, right? It's totally imbalanced, right? So, okay, I can create the offset, but not clear that actually from a common mode or power supply rejection standpoint, I'm going to be very happy. And in fact, by the way, even if you look at the effective resolution of this thing, since I really have this kind of indirect mechanism to create that offset, this turns out to be fairly nonlinear. Okay, because you have to do some fairly, it's not too bad, but you have to do a little bit of complicated math to really map between how much cap you've put here and how much offset you're really creating. So it turns out the thing becomes fairly nonlinear and the step sizes may not be very good. In other words, you may have fairly large steps, particularly at the low end of the range. Okay? So you can do this, not my particular favorite implementation. So let's see, let's maybe come up with another one and see if we can do a little bit better. So again, I'm going to redraw my strong arm comparator here. Okay, so this time around, I'm going to try and maybe be slightly more clever. So this is, let's say, my VI plus. That's my VI minus. This time I'm going to say, well, okay, what's really creating the offset here is that even if I have zero differential input, if there's, let's say, some threshold voltage mismatch, the current coming out of this side might be different than the current coming out of that side, right? So how about I basically just add some variable currents out of here that will try and compensate for the mismatch in current between the two sides. Okay? Right, so as an example, let's say that this transistor here, from whatever reason, had extra current into it. So if I wanted to compensate for that, I would turn on some current on this side so that the two basically balance each other out. Right? Okay, so now it's looking a little bit better. But I claim this is still maybe not the best way of doing things. Okay, and to see that, I'm just going to sort of expand a little bit how you'd really build that variable current source. And I think we've seen this before, but just to make sure it's clear. Right? So the way you'd probably build that variable current source looks something like this. Okay, so you'd have some basically bias voltage that's creating the current source transistors on the bottom. And you just have a bunch of digital switches. Okay? And you tie all those things kind of up at that drain right there. Okay? So, again, from the standpoint of the things we just talked about, what's maybe not so great about this? What am I sort of spending to create this offset? Or what am I adding to create this offset?
Cap.
Yeah, I'm definitely adding cap, right? Because actually, each one of those transistors there has some parasitic capacitance associated with it, right? So if there's a certain amount of range I need to handle, I'm going to add that much parasitic cap on there. Okay, and it turns out actually for this particular implementation, the currents you need to be able to change tend to be quite small. Tend to be like 10, each one of these things might be only about a microamp or so, right? That actually means that even if I make each one of these switches right here minimum size, then just if there's a certain number of these variable current sources I need to add in, I'm just going to have that number times the minimum size transistor times that cap in terms of the parasitics there. And a lot of times that's going to be way, way more, or much, much larger cap than the whole cap you would have had here to begin with if you weren't doing any offset cancellation. Okay, so that's actually also kind of bad. So basically it's tending to add a lot of parasitic cap into a spot where you're very, very sensitive to that parasitic cap. Okay? There's actually one other thing that's kind of a little bit annoying about this particular implementation here. So what else is maybe a little bit bad? And maybe to give you guys a hint, how would you decide what these currents should be? Like how would you, if you were doing the design, how would you pick the values of these current sources? What do you guys think? Like how would I come up with 1 microamp here? Well, what am I trying to do in the first place?
Cancel offset.
Yeah, so I'm trying to cancel what kind of offset? A voltage or a current offset?
Voltage.
Yeah, so what I'm trying to do is cancel the voltage offset, the input refold voltage offset, at the input of these two transistors here, right? Okay, so how would I get from current that I've intentionally injected back to an input referred offset? What do I need to know?
Yeah.
Yeah, I need to know the GM of these input devices. Well, okay. The GM of these input devices, this thing is just a clock here, right? So this is just kind of like shorting it to ground. So the only thing that's kind of setting the GM of these input devices is the common mode of the inputs, right? What happens if that common mode changes? Can I use the exact same current? Or do I actually have to change this current in order to actually create the same offset?
I guess we could try to measure the common mode input.
Okay, you're right. You could try and measure the common mode input and then adjust these currents based on that common mode input. By the way, what you're kind of getting at is that maybe I'll just make the width of these things kind of variable, right? Because if I made this like a variable width, then it'd be like I'd automatically measure the common mode. But bottom line, this is kind of a pain because exactly which setting I need to use really depends on the common mode of the input, and in fact, even on the power supply. Okay? So again, from a sort of circuit balance standpoint, it's not that great because things just aren't very well controlled here. Okay? So again, both of these actually work, but I claim are probably not the best way to do it. Probably not the sort of cleanest place to insert that offset. So now, of course, if I told you about two things that I don't like, I'll tell you about a couple of things that I do like, or at least that I use quite a bit. Not that they're perfect, but they tend to work a little bit better. So it turns out the place that's often the most convenient or that has the least disadvantages for you to actually inject the offset tends to be the preamp. Okay? And if you remember, you kind of needed that preamp in order to do kickback, basically to suppress the kickback anyways, right? So just as a reminder, typically that preamp was going to look something like this, right? Just a resistively loaded differential pair. Okay? So I'll draw in the comparator here too. Right? And so I was going to take that and just feed it into my comparator. Okay, so just as maybe a reminder, why was it that I said that I wanted to build the preamp this way with these resistive loads here? Why was that kind of important?
No noise.
Low noise. I mean, maybe, but actually there was another consideration that was really related to the kickback. Why did I say I really wanted a resistive load here?
Very linear.
Yeah, right? I wanted to make sure that even if I had a lot of kickback over here, I wanted to make sure that basically the impedance that I saw looking back out of that comparator was basically constant on the two sides, right? So that even though I have an input voltage signal here, I'm not really modulating the impedance very much. And therefore, as long as I have this nice linear impedance, all the common mode kickback should remain common mode at the output of the preamp, right? So what that basically told us is we really wanted to have relatively small load resistance. Okay? Well, that's actually kind of nice even from the standpoint of creating offsets too. Because if you think about it, now what we can do is, if we want to create an offset, essentially all we have to do is add in some variable amount of current onto one side or the other. Right, so essentially all I drew here was, if I know, like let's say I want to create a positive versus a negative offset, that's just how I decide which one of these two switches will be on. And then to change the magnitude of the offset, I just tweak this current here. Okay? Again, what's nice about this is that as long as RL is much, much less than the RO of the transistors, which is kind of what I needed to do to make the preamp work for low kickback anyways, then even though I'm adding in this current over here, from a basically imbalance standpoint, I should only have very, very minimal impact, right? Because again, as long as this RL is very small, the only thing adding in that current should change is the ROs a little bit. But if those are big kind of anyways, then I can get still pretty good balance out of doing this. Okay? Does this make sense to everybody? Or? Okay, now, is this perfect, or does it have some sort of disadvantages as well? By the way, this is the one that I use like 90x% of the time, but it's not perfect either. So what's kind of not so great about this? What's the disadvantages? So the advantage is I have pretty good balance, as long as my RL is small. But what's the disadvantages?
Draws current.
Yeah, I'm basically burning power, right? Is that power like helping me go any faster? No, right? It's not helping me go any faster. Is it giving me any lower noise? No, right? In fact, it's actually giving me more noise because I just have this offset current that has noise associated with it that's going to be moving things around, right? So basically, I'm burning power without actually getting any extra benefit out of it, other than just canceling the offset, right? So that's bad. There's actually another sort of indirect way that it's going to force me to burn more power.
Cap loading.
Yeah, I've got some cap loading from these transistors here, right? So that extra cap loading for the same bandwidth is going to force me to also burn more power. Okay? All of that is true. There's one other thing which is maybe a little bit subtle, but it has to do with kind of, it's not necessarily a huge disadvantage, but it has to do with sort of the range of offset cancellation. Okay, so it turns out because I'm doing this, because I'm trying to cancel the offset at the output of this differential pair here, if you guys remember when we talked about slewing, if I look at basically the differential current coming out of the pair versus the input voltage, it's of course going to look something like this, right? Or just as a reminder, this was essentially V star. Well, all I'm doing here is adding in some current, right? So in other words, if I wanted to know what was like the input referred voltage effect, I'm just kind of like walking along this line, right? Well, unfortunately, once I get to V star, this whole thing is becoming highly nonlinear, right? I'm basically totally flattening out this curve. So I don't even really know exactly what the voltage step I'm creating at the input is, okay? So what this basically says is kind of the linear range of offset cancellation is basically tied to the V star of my input pair. Okay, so if I need to be able to cancel really big offsets, I need to make sure I use a big enough V star to actually sort of get the steps that I expected. Okay? It's not that you can't try and add so much current that you're out over here. It's just that obviously things become totally nonlinear at that point. Right? It just doesn't really behave the way you want it to. Okay? But again, this really the biggest advantage of this is that it allows you to maintain pretty good balance. Okay, and that actually tends to be quite important, especially if you're trying to cancel pretty big offsets. Okay? Does this make sense to people, or?
So, in practice, how does that usually work out? Is that
In terms of, what do you mean?
like the sigma variation versus how much cancellation you can achieve, or
Okay, well, I mean, basically, with all of these, essentially you have to figure out, what's going to set how big that DAC is going to have to be from a number of bits standpoint, is again just going to be how big is the sigma of the variation versus how small of a residual offset you want. But so in practice, so actually maybe I'll give you some numbers. So for things like this, people did maybe 3-4 bits of resolution. Okay, so they could kind of, in that previous 100 millivolt example, they'd get about like 15, 20 millivolts residual offset. Okay? Kind of similar for this, and the main limitation here was really just how small can you make these darn switches right here. Okay? For this, people routinely do 8 bits of resolution. In fact, maybe even 9 or even a little bit more than that. Okay? Now, you do have to pay a little bit of power for it, but the overhead is not too bad. So you're probably paying maybe like a factor of 2 or something like that. And with 8 or 9 bits of resolution, that means you can cover anywhere from plus minus 100 to plus minus 150 millivolts of offset, right? And get it canceled to within 1 millivolt of residual error. Okay? So in practice, this actually works quite nicely. It's not that it's free, but it works pretty nicely. Okay? So the question, of course, again, ends up just being how much power do you spend for it? And, okay, I said it was good from a balance standpoint, but it's not perfect. So you'd have to go back and just really check, okay, how screwed up is my PSRR or my CMRR going to be once I've actually injected that full offset into the system? Okay? Yeah?
What's the signal and the inverter doing?
Oh, so this is just the sine bit. It's just basically choosing, if the sine bit was a 1, I turn this switch on, and I'm going to be pulling current out of this side, right? If the sine bit is a 0, that switch is off, this switch is on, and I'm pulling current out of this side. It's just really telling you what's the sign of the offset. right? Because if the offset is positive, you want to pull current out of one side. If the offset's negative, you want to pull current out of the other side. Okay? And by the way, this sign bit would just be like coming from your accumulator. Right? You just obviously have to build something that has a sign associated with it, but that's not too big of a deal.
The magnitude's like mirrored from a bank of switches.
Exactly. So essentially this variable current source that I drew down here, that could basically be this same variable current source right here. Okay? It's just that what's nice about this, if you build this the right way, you can keep this switch here in saturation. So that means that even though there might be a lot of cap right there, you're isolated by sort of the RO of that switch. Okay? So that means that you can afford to actually put a pretty high resolution DAC there. Now, again, you have to be careful because that does mean that if, from whatever reason, which unfortunately will be the case, there's a little bit of noise on the power supply of that sign bit, right? That will just show up directly at the output, right? Because if I have a really big cap right there, it just kind of looks like a common source amplifier from the standpoint of any noise I put on that control signal right there. Okay? Is there a question or? No. Okay.
Do they ever like mirror the current, or do they just put the DAC at the bottom?
Oh, I see. So you're asking basically, could you just put the mirror device right here, and then essentially, or I should say, put the current source, and then essentially have the DAC sitting like this?
Right.
That's what you're asking. Okay, that's a great question. You can do this. This tends to only work up to about 5 or 6 bits, though. Because the problem is there's mismatch between these two, right? Because there's mismatch between the mirrors here, what will end up happening is that particularly when you go to the very low currents, right, the very small steps, that mismatch will cause it so that like if you go from 0 current to any current, you get this huge jump, right? Because you go from like not doing anything to just all of a sudden you get that full offset, right? So you can indeed do this, but you just have to be really careful because unfortunately the step sizes for this, the worst case step sizes, tend to not be so good. And if you try and make it really good, that basically means this current ends up, like this device ends up being huge, and then it's not clear that that's any better than just using the DAC directly at that spot. But that's a very good question. You can indeed do something like that. Okay, great. So like I said, this is kind of the one I use most often, but it's not perfect. And in particular, it does really cost you extra power. Okay? So there's one more implementation that has become somewhat popular, but not necessarily ubiquitous, but is kind of an interesting one to look at. And the main thing that this goes after is to actually not spend or try to not spend any extra power. Okay? So with this one, what we're going to try and do is make it so that we always spend the same amount of power, and all of that power always helps us from the standpoint of actually getting gain or GM out of our devices. So the way this thing is kind of built is sort of interesting. So what I'm basically going to do is imagine I took my differential pair, and instead of building it as kind of a normal differential pair, I'm going to split it up in kind of a little bit funny of a way. Okay? So I'm going to split it into like 2 differential pairs. When I split it, what I'm going to do is, on one of those differential pairs, I'm going to make the device that's connected to Vn plus really, really big. Okay? And the device that's connected to Vn minus, really, really small. In the other differential pair, I'm going to do the opposite. Oops. So basically, I'm going to connect the device that's small to Vi plus, and the device that's big to Vi minus. Okay? Now what I'm going to do, I'm just going to connect the outputs of those 2 differential pairs together, which is kind of like saying that I've just split it into 2 pieces, and then connect them to a single shared load resistance. Okay? So let's even call this I1 and I2. Okay? So, and by the way, just in case you're curious, this is coming from a guy named Brian Casper, and it was published in JSSC in 2003. Okay? So the idea here is actually kind of simple. So let's just pretend for a second that we put all of our current in this differential pair and none of it over there. So if I put all of my current over here, my VI plus is much, much stronger, right? So which way am I pushing the offset? What am I doing to the offset if I push all of my current onto this side? What do you guys think? Let's maybe give some specific numbers. Let's say that this thing is like, I don't know, 10x bigger than that one. So let's actually maybe even give some specific, ideas here. So let's say that when I do that, let's say that I have like plus 1 millivolt over there. How big of a signal do I have to put on VI minus in order to like balance the thing out? In other words, have the same amount of current coming out of the two sides. Just ballpark.
+3.
Oh, you did a square root. Okay, let's assume somehow magically the GMs are the same, which is not actually exactly correct. You're right. But what I was actually going to go for was minus 10 millivolts. Right? I mean, you're actually probably right. It's probably more like -3, but don't worry about that. I'm just trying to figure out the sign of the offset right now. Right? So in other words, because this device is so much bigger than this one, if I want to get the same current on the two sides, right? And actually, I guess technically you're right, so I should call this plus 10, right? Essentially what I have to do is I have to put a much, much bigger signal on the VI minus side than on the V plus side. In other words, I'm creating a negative offset, right? Because only when I have really large negative signals will this thing become balanced, right? So now you can kind of see the way this thing is going to work is if I want to create an offset, I just steer current between these two differential pairs. Right? So if I put a lot of current on this side, I'll have a large positive offset, right? So in other words, essentially the whole idea here is just that there's going to be some fixed total current that I'm just going to be splitting between I1 and I2. Okay, and as I move more of the current to one side versus the other, I'm going to be shifting the differential offset. Okay? So, kind of, yes. So it's actually, you could almost argue that it's kind of like a Gilbert quad. It's just that I'm intentionally offsetting the sizes of the two differential pairs. Right? Because what I'm really trying to do is just move the offset around. Okay? But you're right, it is actually kind of a lot like a Gilbert quad. Okay? For those of you guys who are familiar with that. So what's nice about this is that, notice I'm always using all of the current, right? All of the current is flowing through my differential pairs. So I'm always getting that gain, right? I'm not like using any current just to have offset. But unfortunately, there are some, few things that are bad news about this. So again, the good news, I have pretty good power. What's the bad news? Yeah, the balance is not that great, right? Because in particular, imagine that I steer all of my current onto this side. If all of my current is onto this side, well, clearly I have a totally imbalanced circuit, right? Because I have one huge device and one tiny device, and ain't no way those two are the same, right? So that's actually the biggest bad news about this, is that particularly over large offset range, basically your balance is not that great. There's one other thing to kind of keep in mind about the design of this thing. So what's really sort of setting the range of offset you can cover by this? Like by design, what do you have to do if you want to get a larger range of offset?
Make the difference very big.
Yeah, so you basically have to make the sizing ratio big, right? In other words, the offset you can get, kind of conceptually, is still limited by the difference in V stars. Right? Because you can kind of think about it like that's really the only mechanism we have available to actually create this offset here. So if you want to get really big offsets, that tends to mean you need very large sizing ratios there. And if you need really large sizing ratios, again, you might just end up with this is a minimum size device, and this thing has to be some number larger than that, and that just fixes how much power you have to spend. Okay? even if you could have gotten away with something much smaller by choosing your V-star independently or choosing the device size somewhat independently. Okay? Does this make sense to everybody? Or? Okay, so like I said, I tend to use this, but it does have the penalty of power, so this one is also actually a pretty interesting solution. You might actually be so good that somehow you've managed to knock off all your offsets. You only need a couple of bits. So maybe even these solutions will kind of work for you. But if you're not sure, this is a pretty reasonable sort of place to start from. Key is really make sure you understand sort of how does the range you need to cover translate into how much power you have to spend, what's the parasitics you're going to be placing on this thing, and so on and so forth. Okay? So the good news is, from the standpoint of the project, you've now got everything you need to know to be able to actually complete the project. So before we kind of move on, are there any questions on this? Or?
So does your noise change a bit over offset voltage?
Yeah, absolutely. Right? So particularly for something like this, you can imagine if I'm injecting a really large offset, that means I have a really large current. That current, of course, always has some noise associated with it. So this has the sort of bad, quote-unquote, characteristic that it's most imbalanced when you have the largest offset. It also has the most noise, and it also burns the most power, right? Now, that's kind of life, because if I have a big offset, I have to do something about it, right? But that is essentially exactly how this thing works. So in particular, again, with your project, you should be evaluating everything in those worst-case conditions. So you should really skew things as much as they could possibly be skewed, and make sure you still meet all the criteria you want under those conditions. Any other questions? Or? Yeah?
So usually you need to balance both the offset of the comparator and the...
Ah, great question. So you're absolutely correct, right? Because we've been talking about the offset of the comparator itself, but hey, this preamp has offset. And darn it, your equalizer probably has offset. And darn it, whatever you put in front of the equalizer has offset too, right? So in fact, if I just do this thing here, then you're absolutely right. This thing not only has to handle the range of offset from the comparator, has to cancel the preamp, it has to cancel the equalizer, and so on and so forth. So in fact, what you sometimes will end up doing, just kind of like we had talked about, the multi-stage offset cancellation back over here. Right? So here we did this with capacitors, but you can imagine if we have these trim circuits, if you have a lot of stages, what you might indeed do, and let me just draw that as differential. What you might indeed do is actually add trim circuits in multiple spots along the chain. Right? So you might have one trim circuit, let's say, over there, and another trim circuit, let's say, over here. Right? For basically the same reason, because you just want to make sure that, okay, maybe I have a lot of gain in front of here, and so it would be just impossible for me to cancel the amount of amplified offset I would have gotten by the time I got to this point. Now, obviously when you do this, you have to be a little bit more sophisticated with the cancellation loop, right? Because you have to figure out, okay, probably I have to cancel this guy's offset first, then come back and cancel this guy. But you can indeed do all of that, right? You have to think about it a little bit, but it can indeed be done. So if you need to do something like this in your project, that's also basically fine. You should just think a little bit about practically how you'd really do it, but that's also fine from my standpoint. That's a great question. Any other questions related to this? Or? Okay, so I'm sure a whole bunch more questions will come up once you actually start trying to build these things. So feel free to come by and bug me. But if not, what I want to do is actually go ahead and move on to the next set of slides here. So basically one of the, and probably the last really main topic we're going to cover is, we've been talking a lot about these switches and how they're really nice for building these switch capacitor circuits. And in fact, we even talked about them from the sort of standpoint of offset cancellation. And I kept mentioning how, well, these switches aren't really ideal. They cause like glitches and errors and things like that. Well, so now we're finally really going to see, okay, what's really going on with these switches? How do you really build them? What are the key issues? So, of course, as usual, we sort of start out with just what is it we ideally want and what is it we really get? Okay? So, of course, ideally what we really want is when I draw these switches, I want it to just grab exactly the value of V in, exactly at a particular point in time, right? And I want it to do that without disturbing anything else in the rest of the world. I just want it to exactly grab that value. Well, unfortunately in real life, of course, things aren't quite that simple. So in reality, what you're going to get is a whole long list of bad things. First of all, as we sort of talked a lot about way back in the beginning of the class, right? Anytime you have some resistance or something driving a capacitance, you can never get exactly the value of the input because there's always some thermal noise, right? That thermal noise is always going to be set by kT over C, okay? So if you want some very, very low noise type of system, your only choice is essentially to make the capacitor sufficiently large, okay? Well, once you've done that, again, unfortunately, these switches, which by the way really will be built out of MOS transistors, they always have some on resistance associated with them, right? Even when they're on, they're not really just a short. There's some resistance there. Well, that means that if I basically had a certain size capacitor, then if I have a certain resistance here, there's only a certain bandwidth I can get through this sampling network, okay? And of course, if I have to increase the size of the cap, I'm probably going to have to size up my switch to get a low enough resistance to maintain that bandwidth, okay? Now, in fact, it's going to turn out that life is even more annoying than that, because right now I've sort of been talking about this resistance as if I knew exactly what it was. Well, turns out that resistance actually depends on the input voltage. And we'll see exactly how that happens in 1 second. But because the resistance actually depends on the input voltage, that means we actually have a nonlinear circuit. Well, anytime you have a nonlinear circuit, you could actually basically get distortion, meaning that you don't just linearly change things at the output. You actually are creating new frequencies, you're like distorting the waveform, all kinds of the fun stuff that, if you're really like trying to build oscilloscopes or ADCs, you spend almost your entire life just fighting with it, okay? So we'll talk some more about that. The other thing that is actually kind of the main thing that's responsible for some of these glitches we've been talking about is so-called charge injection, okay? So the idea here is actually quite simple. So if I take this switch here and I kind of draw our standard, MOS side view, when the switch is on, there's some charge inside of that channel, okay? Well, when we want to turn the switch off, that charge has to go somewhere. Unfortunately, it can't just jump into the space or ether or anything like that. It actually has to flow out of your switch, okay? That means that some of the charge is going to flow over there, some of the charge is going to flow over there, and guess what? That charge some of that is going to show up on the spot where you actually want to sample your signal. It's going to show up on this cap right here. Well, it turns out that charge is going to basically, first of all, it's going to cause a voltage error. Second of all, that voltage error is actually going to depend on the input signal in a perhaps nonlinear way. Okay, so again, this is going to actually be a source of basically distortion. The last thing that actually we're not going to spend a whole lot of time on here in this class, but is definitely something you need to keep in mind, is even though I keep always drawing these clock phases, when I draw those waveforms, I keep drawing things that look like this. Well, again, life's not that good, right? In fact, those waveforms always have some slope on them. And even worse than that, you can never say exactly when the thing actually was going to go high. There's always some jitter around a particular clock edge, okay? Well, what's bad about that is that if there's some jitter on the clock edge, if you sort of think about it, imagine my input signal is doing this during the time I'm trying to sample it. Well, if my input signal has a big slope on it, and I'm not sure exactly when I'm actually going to take that sample, you can imagine if I was supposed to sample it here, but I actually sample it right there, guess what? I actually sample a different voltage, right? So in fact, if you look at really high-speed applications, a lot of times the biggest errors you have to worry about have nothing to do with your circuit itself, but have everything to do with how precisely are you actually doing the sampling. In other words, how precisely can you set up that sampling clock to really grab the data that you wanted, or to grab the voltage that you wanted. Okay? So what I'm going to do in this lecture is kind of walk through a few of these considerations and come up with some simple models that we can use to understand how big those effects will be, as well as look at a few circuits that people have come up with over the years to try and mitigate a lot of these different effects. Okay? So first of all, let's just maybe start off with kind of basically what's going to happen from a bandwidth standpoint, which in particular really just has to do with how much resistance are we going to get from our switch. Okay? So let's just basically draw like the simplest switch that we might think of to use for our sampling. Okay? And that might be just something like this NMOS switch right here. So in particular, while I'm sampling the thing, in other words, while the switch is on, probably what I'm going to do is just connect that gate to VDD, right? Well, so this kind of works, but obviously has a pretty direct implication on what the resistance is actually going to be. Because, as you guys hopefully either already know from another class, or you can figure out just by kind of thinking about it, if I look at the resistance of that transistor as a function of Vin, what's basically going to happen is that transistor is going to be pretty good at passing low input voltages, but really crappy at passing high input voltages. In other words, my R on versus V in curve is going to look maybe something like that, right? By the way, just as a reminder, why is that? Like, what's going on there? Why is it that this switch really sucks when V in, as an example, is close to VDD?
VGS gets small.
Yeah, its VGS gets tiny, right? Because when Vn is up close to VDD, it has a basically nearly zero VGS, and so of course I get basically no current flowing through the thing, right? Okay. So what do you guys think I'm going to try and do to fix this? What I'm going to try and add to my switch to make it so that I can really get signals all the way from 0 to VDD? PMOS. Yeah, I'm going to add the PMOS, right? I'm essentially going to make this a transmission gate. So I'm going to have something like this. And of course, if I have a PMOS, then I get kind of like a reversed curve. I get something that looks like that, right? Where essentially, at high voltages, I get low resistance, and at low voltages, I get very high resistance. So this certainly helps quite a bit, but unfortunately, even that is not quite perfect. And really, the problem you tend to run into is that if I look at like the parallel combination of these two things, what I'm going to get is something that kind of looks like this. Okay? Now, it doesn't look so bad here, but just to make it maybe more obvious, let me just pretend that I actually drew this on a log scale. Okay? In other words, right around that point there, which unfortunately tends to be right around the middle of the supply voltage, you tend to get basically a much, much higher resistance. Okay? Because what happens is right around that middle point right there, basically both the NMOS and the PMOS essentially have pretty low VGS on them, right? So unfortunately, both of them tend to have a pretty high resistance at that point. So yeah, I put two of them in a parallel, and so maybe it's not quite as bad as one of them individually, but neither one of them is really great. This is actually a particularly big problem when, and actually in modern technologies, when the VDD relative to the threshold of the switches is not that big of a ratio, right? Because if the VDD is only like a couple VT, you can imagine that right around VDD over 2, both switches are essentially off, right? So you can get really, really big resistance right at that point there. Okay? Now, by the way, why is this really particularly annoying? Especially from the standpoint of like getting circuits that have as large of a swing as we can possibly get. Why is this bad? So if you wanted to build an amplifier that has like as large of a swing as you can possibly get, where do you usually want to bias the output of that amplifier?
VDD over 2.
VDD over 2, right? Because you want to be able to swing a full VDD over 2 one way and a full VDD over 2 the other way, right? Well, guess what? this usually happens to sit right around VDD over 2. Okay, so it's kind of a big annoyance because right where you'd like to bias things from a swing standpoint is right where these switches tend to not work quite as well. Okay, now there are some tricks that we'll talk about a little bit later that can allow us to sort of get around this, but it's definitely something to keep in mind because this can very easily sort of come and bite you if you don't think about it. Okay, so definitely keep that in mind. So we've been so far talking about sort of the on resistance of the switch, but actually you care about what happens when the switches are off also. So for now I'm just going to draw, the NMOS, but we can imagine that we would have had the PMOS there too. Okay? Well, so when the thing is off, essentially what we're going to have is the resistance is just sort of set by leakage, right? So we already talked about if I was waiting like a really, really long time, then basically my sampled voltage could actually leak away. But there's actually sort of something else that you might care about, which is even though it's only leakage, my input signal might still be moving around quite a bit, right? And if I really wanted to sample it at just one spot, I want to make sure that this thing over here doesn't keep moving around because of the input signal. Okay, well, it turns out if the leakage is not, really, really small, you might still get actually quite a bit of coupling onto there. In fact, in particular, if you have any stray capacitive coupling like that, you might even get really, really big changes in the sampled voltage because of the fact that the input is still moving. Okay? So I think we're basically out of time for today, but maybe just as a little brain teaser for you guys to go at home. There's one small modification you can make to the design here that actually largely gets rid of both of these problems. Okay, so if you're interested, think about it some more, and we'll pick back up with that next time. So see you guys then.